Again, I have this little camera here on top. My old camera's working. It wasn't doing that before. That's good. So let me just, sorry about that. Let me hop back in here. So I'm going to fire this up. So again, just to recap what we're looking at here. I'm going to take a look at the R project. So again, you go to the web page, and again, you have this guide. This was sent out to everybody. You click on the download link. You can choose one of the downloads. You can say download from Brazil. And then you can choose your operating system, Linux, Mac OS, Windows. I use Windows, so I'll click on Windows. Install R for the first time. And then you can click here, and it's going to start downloading. Now I've already downloaded this and installed it, so I'm just going to cancel. All right. So let me switch over here to the desktop. Try it one more time. Messy desktops. No, not showing in there. So let me do this. I'm going to fire up R anyway. And there we go. Back online. So again, what R is, it's basically it's a sort of a script type program. You enter in things, it calculates things for you. It can graph, it can do a lot of cool stuff. Again, programming going to be a big deal, especially when you get to your 4-year program. They're going to have you do this if you're in science, if you're in engineering. Programming just a huge, huge thing. So if you want to just figure out what's 7 minus 2, type in 7, subtract 2, hit enter, you get 5. If you do multiplication, this is 7 times 6. This asterisk or shift 8 was times. Hit enter, you get 42. So the thing we want to do is we want to store numbers and variables. So if we let x equal 3, like that, we type x and hit enter. And the reason I get these little spacings here is I hit enter, it moves me to the next line. If I hit enter, they say x has the value of 3. So if we say x plus 2, we get 5. X plus 10 or 12, we'll get 15. And here's x plus 10. So again, x is still 3, so x times 10 give us 30. And so that's kind of how R works. Now what we want to do is we want to store a bunch of numbers in R. Now, so we're going to use something called the sequence function, SEQ. You have a start number, an end number, increment. And so the start number is going to be the farthest left number on the x-axis. The end number is the farthest right number on our x-axis. And then the increment, we're going to divide up the x-axis between the start and the end. And we're going to space numbers using this increment. So for example, we start at -10. We end at 10. We have an increment of 1. This is going to give us all the integers from -10 to 10. And so there you go. Now you can get kind of crazy with this. Let's say go 0.5. So now you've got more numbers generated. -10, -9.5, -9, -8.5, and so on. We get 8.5, 9, 9.5, and 10. Or you can do something like this. Really generate a bunch of numbers between -10 and 10. And there we go. So to graph what we're going to do, we're going to generate a bunch of numbers. So let's say we're going to store these in an independent variable x. Let's go with the sequence starting at -10, ending at 10, and each number is spaced out by the number 1. So if I type x and hit enter, there's all those numbers. They're all there. Now, we can create a dependent variable y, which is x plus 1. So if we hit enter, x hasn't changed. X is still the same. But y, take a look at y. It contains the numbers from x, but those numbers haven't increased by 1. So x went from -10 to 10. Y goes from -9 to 11. So x is going to be, we're going to treat this as our independent variable, and y is dependent because it depends on the values we chose for x. Now, to plot this, we're going to use what's called the plot function. And again, this is all in that guide that was sent out. If x, and that's what it looks like. Now, these are just points. To make this into a solid line or a curve, property type. Type is equal to L. We put the L in quotes. But if we add this little thing, that's going to give us a solid line. Now, finally, if you want an x-axis and a y-axis, you're going to use this command. This is kind of strange, but after you've graphed your line, it's called AB line. Now, for the y-axis, it's a vertical line at x equals 0. And for the y-axis, horizontal line at y equals 0. And so there we have our axes. So that's sort of the introduction to graphing with R. Now let's do something a little different. We have our x. Say y is equal to x squared. So we could just do this for x squared. This here means exponent. So there's y. If you check y, we're going to get that. So now let's plot x and y. There's some points. Let's plot them again, but let's make this a solid curve. So we use that type equals L in quotes. And let's take a look at a y-axis. So we have a vertical line at x is 0. And a x-axis is a horizontal line at y is 0. And so there's the graph of our parabola. Now, the thing that's of interest in section 1.4 are windows. And so the way we're going to do windows, we want to zoom in on this graph. So we're going to add some properties to plot. So here's a plain plot. And then this one's a little bit enhanced. We have the line here. This gives us solid lines or solid curves. We're going to do something with the window. It's called xlim and ylim. And we have to give xlim and ylim 2 numbers. So instead of putting a closing parenthesis, I'm going to put another comma. So xlim, we need to give it 2 numbers. And we have to do what's called a C. Go C, and let's say we're going to do -10 and 10. What does this do? Well, xlim could stand for limits on the x-axis. So this here is the left limit. this here is the right limit. So the limit for our x-axis in our graph, -10 to 10. Same thing for the y-axis. We'll do -10 to 10. I'm going to put one more parenthesis because this plot, this is the opening parenthesis, this is the closing parenthesis for plot. So hit enter, and this is what I've got. So the x-axis values are listed here, and the y-axis are listed here. Now let's put in that x-axis. So the x-axis is a horizontal line at y = 0. Again, we use this strange command, AB line. You can actually combine these. You can also put the v = 0 for the y-axis. There you go. And so this is a change in window. Now, why this is important, and we looked at this a little bit last time. Let's see, I'm going to do a sequence from -10 to 10, really get this sort of kind of a fine gradation. So we'll do that. Do an increment of 0.01. So x, got a whole bunch of values. Now y, do sine of 1 divided by x. In fact, I'm going to do one little thing here, though. My x, this is kind of a thing. I want to equal to itself plus a tiny number. So what this will do is it'll take my original x, these values here, add a tiny number to it, and then store these in x. We're going to sort of re-identify x. So now if I look at x, got this. This is going to keep me from dividing by 0. So y, let's let y be the sine of 1 divided by x. So that being the case, let's plot x and y and just see what it looks like. Wow. Okay. Well, let's plot it again, but let's use a line. Let's have a curve here. There we go. And then I'll put in some, let's see, horizontal for the x-axis, vertical for the y-axis. And I can even put in a color here. Color equals red. So our graph, if we look at it from this distance, it looks like sort of like 1 over x, but then there's some weird stuff going on in here. So if we want to zoom out, I'm going to do xlim equals -10 to 10. Ylim equals -10 to 10. And so we've got something like this, and then put in those axes. There's an x-axis, there's a y-axis. So if you zoom out, well, it's kind of not really like 1 over x. It actually seems to have a bottom here, and then a top here, and then it just gets really funky in the middle. So let's really zoom in. Or x or y. We want to connect all the points. And let's really go small. Let's go -0.1 to 0.1. And for y, -0.1 to 0.1. Wow. Okay, that's kind of hard to make sense of. But then we can Put in our lines. Give this a color, call it red. So the point of this exercise is that as you zoom in and out, you're going to get very different sorts of pictures of your graphs. So to study your graphs, to be familiar with them, you want to be able to graph these and sort of take a look at what's going on. I'm going to do one more with this. Let's see, we're going to do the sequence. -1 to 1. Go this way. Ooh, I'm using the old sequence here. Let me do this. Old format rather. So this happens here. This means there's a division by 0. So what I'm going to do is I'm going to take my x, it's going to be equal to itself, plus a very tiny number. It's a little way of getting rid of zeros. Not always the good idea, but I think for this example, it should be all right. You want to be careful, especially if you're working with data. You want to get permission before you do something like that. You don't want to be modifying your data for mathematical purposes. There's transformations of data, but that's a whole other conversation. Generally, I would not advise this. I would not advise that. But for this example, it's going to be okay. X, Y type equals L. And then let's put an xlim, -1, 1, ylim, -1, 1. And we can give this a color too. We can call this red. Let's put in our axes. We have an x-axis at 0, vertical y-axis. And there we go. And so you could take a look at your graph here, and then if we zoom in, and here's sort of a professional tip. If you hit the up arrow key on your keyboard, and if you hit it again, it'll keep giving you all the previous things you entered. If you hit the down arrow, eventually you'll cycle through those to the beginning, or to where you left off rather. So I'm going to hit my up arrow and change this to 0.1. Put in the axes. So just again, just to illustrate that when you play around with the window, you're going to get different pictures of what the functions are looking like. And so that's something you can do. If you don't have a graphing calculator, you can use R to graph your functions. It's free, and you can go to the download page. That is the R page there. It's used a lot in statistics. It's really big in statistics, and you can do a lot of cool stuff with R. You do like 3D graphs and things like that. So anyway, and so that's R. So any questions about that? All right. So what I'm going to do now, it seems like I got my old camera working again. That's kind of neat. So the other thing to mention for section 1.4, the other issue is that some graphing packages, if you are doing something like you're using something off the internet, or maybe some calculators, you want to be careful. The book gives kind of an example. So not all functions will graph well. And the example they give in the text is x to the 1/3. And this one's also in that guide that was sent out. I know in R, if you try to graph y equals x to the 1/3, what you're going to get is something that looks like this. It looks like a square root function is what it is. What you're missing is the rest over here. And for reasons that are particular to R, it's not going to allow you to input negative values for this function. This is really strange because you can take the cube root of negative numbers, and that's what this is. This is a cube root. So one way you can get around this it's kind of a clever fix. But there's a trick you can use, and it involves your absolute value. Let me see how they set that one up. So you have your x to the 1/3. What you can do to fix this problem, and it's not really one, but for positive values of x, if x is positive, the absolute value of x is just x. So x divided by itself is 1. So this is for x greater than 0. Now, if x is less than 0, well, this will be positive, but this is going to be negative. So you're going to get negative 1 for x less than 0. So that's what this whole thing is doing here. And so then what you can do, you can multiply this times x, absolute value of it, to the 1/3. And that would fix this. That's what's going to get you out of trouble. So what you end up doing, and it also depends on the program. If you take the cube root of this negative value, it might say that it doesn't exist, and that could just throw everything off. This kind of thing might create, it's like, it treats it like taking the square root of a negative number, which it shouldn't be doing. So you can take the absolute value. You've got your 1/3. So you're going to be getting the positive here. And then for negative values of x, this will become a negative 1. And what that's going to give you is the rest of your graph, except for one place. You're going to have a hole at the origin. So this is something to keep in mind. And again, all of this is in that guide that I sent out. So just kind of keep an eye on this. So you can get some, I don't think this is a problem for graphing calculators, but if you're working with some programs, they might not like to take roots of negative numbers, period, which is unfortunate. So the way you fix that, make sure you're not taking roots of negative numbers, but then you can take x divided by its absolute value, and that's going to fix your problem, at least in this particular case. So that's all there really is to say. But that's really it. For 1.4, it's just adjusting windows and just being aware that sometimes you don't get a complete graph. If you are not using a graphing calculator, if you're not using something online, I definitely recommend R. It's a great little program. You can do a lot of data analysis with it. Like you can import different like CSV files that contain all kinds of data. You can graph that data. It's pretty cool. But I just wanted to show you R. It's free. That's kind of the neat thing about it, which is really nice. So if you want some free graphing software, you've got R. So that's 1.4. I just wanted to mention that, show you what R was. Again, if you need to do graphing, if you need to do 3D graphing, like in Calc 3, R can do that too. It has some packages that let you do that. So section 1.5, we're talking about exponents. And so with exponents, I'm just going to review the properties. And there's a bunch. I'm not going to review all of them. But we're going to have this. We might get pretty much all the algebra properties here. It's kind of what calculus does. So let's say we have this. A to the x, a to the y. We've got the same base. A to the x plus y. We add them. So I'm going to get rid of this. It looks like multiplication. So that's a property. Call this number 1. Number 2. Let's say we have a to the x with y on the outside as an exponent. Well, now we multiply the exponents. Now, let's say we have a times b to the x. We're going to distribute x as an exponent like so. Now let's say a and b already have exponents. Well, we're going to distribute z as an exponent. A to the xz, b to the yz. Questions about that? All right. So this is just going to be a short list you can keep with you, just to kind of, all right, I forget how to handle these exponents. You can pull these lists up and like, oh, okay, that's what you're supposed to do. Got it. Well, I'm going to keep going. There's more. So a to the x over a to the y. So now we're dealing with divisions. A to the x minus y. And then a over b to the x, this will get distributed to a to the x over b to the x. Now, if a and b already have exponents, we're going to distribute the z as an exponent. And of course, to keep in mind, it goes the other way. If you start out with this, you can rewrite it as this. If you start out with this, you can rewrite it as that. Questions about that? And again, these have the same base, but these have different bases. All right. So sort of a crash course in that. So other properties with exponents. Well, let's talk about the meanings of exponents. So a to the n is equal to a times a times a. Exponents mean repeated multiplication. So there are n of these a's multiplied together. So for example, if you take just 5 cubed, 5 times 5 times 5, that's what they're getting at. Now, negative exponents. So one thing, pardon me for just a second. Battery was dying. So let's say I have a negative n for n greater than 0. So n's a positive whole number, and it has a negative sign attached to it. Well, this is equal to 1 over a to the n. Now, if we have something like this, this is equal to just a to the n. So when we have our negative exponents, they basically flip things. If a to the negative n is what we've got, we flip it to get a to the positive n, or regular n. If we have 1 over negative a to the negative n, we flip it to get a to the n. And that's it. So, fractions. So we saw this a little bit earlier. A to the 1 over n is the nth root of a. So x to the 1/3 is really the cube root of x. So another one we can do, and we saw this a little bit earlier, a to the p over q. We can write this 2 ways. This could be a to the p, and then we take a cube root, or q root. Or we can take the q root of a and raise that to the p power, or the p exponent. Either one will work, and usually we choose one or the other based on convenience. So those are the things with fractions as exponents. If a is not equal to 0, then a to the 0 is equal to 1. And for any a to the 1 equals a. So those are the main properties of exponents. You've ran into these in algebra before. This is just sort of a crash course of just sort of bringing back some of these properties. The thing to look for, if you look on page 35, page 34 and 35, they mention these in the textbook. So I'm just sort of going over them, bringing them back. One thing I want to look at is graphs. Graphing y equals a to the x. And we're going to consider two situations where a is greater than 1 and then a is between 0 and 1. We're not going to consider a negative base here. We're going to consider just positives. So let's take a look at a greater than 1. So the example I'm going to use, say a equals 2. Now I'm going to generate some values. You do an x, y. And for working with logarithms and exponents, I'm going to be using these values for x, and then we get to logarithms, I'm going to use the same values for y. But here, I'm going to erase this so I can do the calculations. So if x is negative 1, we're looking at y is 2 to the x. So if x is negative 1, we're going to flip this to get 2 to the 1. And that's that rule with negative exponents. And this is just, well, anything to the first power is itself. So we get 1/2. Now x is 0. Well, any non-zero number to the 0 is just 1. So we get 1. Finally, y to the 1. Or 2 to the 1. Well, 2 to the 1 is just 2. Any number to the first power is that number. So we get 2. So now we're going to graph this. So there's 1/2. So our first point's negative 1, 1/2. Point there. 0, we've got 1. And at 1, we're going to have 2. So if we connect these, what we're actually going to get is a graph that looks like this. So in general, actually, I'm just going to say this, but in general, for a greater than 1. Now let's take a look. We've got 1 and 2, 0 and 1, and negative 1, and 1/2. So what's going to happen is that in general, if your base is greater than 1, your graph is going to look like this. So -1, 1 over a. Just like we have -1, 1 over 2. 0 and 1, that's always going to be there. And then we have 1 and 2, or 1 and a. So that's what our graph is going to look like. Questions about that? All right. So that's if a is greater than 0. I'm sorry, greater than 1. Now let's look at a if it's between 0 and 1. So in this case, a could be like 1/2. So let's go with that. Now again, I'm going to use these same values. -1 for x, 0, and 1. So let's do the math on this. So we have 1/2 to the -1. To make this positive, do this. And any number to the power of 1 is that number. And then 1 divided by 1/2, that's going to be 2. Now to the 0. Well, anything to the 0 is 1. So that's just going to be 1. And then finally to the 1. Well, that's just going to be itself. So this is what we're going to get. -1 and 2, 0 and 1, 1 and 2. So if we graph this, so -1 and 2, 0 and 1, we got 1/2 and 1. So what we're going to get is something like this. And this is actually, I want to make a note. The x-axis here will act like a horizontal asymptote. This will not cross the x-axis. So that's what happens if the base is between 0 and 1. Now you might ask, well, what if the base equals 1? Well, I mean, 1 to any power is just going to be 1. It doesn't change anything. You're just going to get a horizontal line at y equals 1. So that's why we skip 1 as a base. You're bigger than 1 or between 0 and 1, but you're not equal to 1. Just a flat line at y equals 1. Nothing exciting there. Same thing with y equals 0. though we have to be careful that when x equals 0, 0 to the 0, we usually consider undefined. So we try not to do anything with 0 to the 0. But again, excluding that, you just get this flat line at y equals 0. Not very exciting. The reason we don't use negative bases is that as x changes values, sometimes you'll get an even root or an odd root, even root or odd root. And when that happens and you have a negative base, you could be trying to take an even root of a negative number, that negative base, and that's not going to exist. So you would get a graph with a whole bunch of holes in it is what you're going to get. So we're going to try to avoid that. That could be a big problem. So we're going to avoid those kinds of things. So anyway, in general, what this looks like. So when a is between 0 and 1, in other words, a is a small fraction or a is a small decimal, that's what we're going to get. So we have -1 and 1 over a. Again, 0 and 1, that's going to be there. And then we have 1 and a. So those are the 3 points that are going to be on that graph. Now, a special kind of function you'll see here. Let's see. We get a decimal approximation, yeah. It's e. So this is one we spend a lot of time with. And there's a lot of reasons for this. E is approximately, well here, it's going to be this. This is going to have meaning in just a little bit. That's going to be chapter 2. Goes on forever and ever. What this is saying is this. If you take this little expression and you keep picking bigger and bigger values for n, let n be 1,000, let it be 1,000,000, let it be 100,000,000, let it be 1,000,000,000,000, the number that comes out of this, like 1 plus 1 over 1,000,000,000,000, and then take that, raise it to the trillion power, you're going to get something that's getting close to this. It comes up in areas, for example, with finance. I'm going to do an example actually with finance here. There's a thing they use here that you run into called the compound interest formula. And it ultimately you can convert it into this. And I'm not going to go into how you do that. I could do it just for the sake of time. But here, I'll do an example with the compound interest formula. And this is one of the things they had to work on in the text. And the formula they have is this. Well, I don't give you this one. I give you one sort of like it. Ooh. Can you see what's going on?
I could earlier, but not anymore. I don't know if it's just me or...
Let me try something. Is that better?
Yes.
Oh, okay. Yeah, sometimes with these cameras, you have to just switch them on and off, and they'll start working again. So this is what's called the compound interest formula. And the way this works is you put money, say, in a savings account. And you typically think that when you're charged interest for money, what interest is basically rent. Someone's renting your money. So interest you can think of it as rent that you pay on borrowed money. And the reason you can think of it like this, if somebody lends you money, they can't use it. You're using it, and they'll get it back when you pay it back. But they've kind of had to go without. So they'll charge you interest or rent on that money that you've borrowed. In a savings account, when you put money in a savings account, the bank isn't just holding on to that money to protect it. They actually use it. What they'll do is they might use it for investments, they might use it for loans for other people. But that sort of thing, because they're using your money, and since you don't have it, they're going to give you interest for that. So that's sort of this idea of why we're concerned about interest. So either you're giving someone money for a while, like a bank or something, and they're going to pay you interest on that, or you're borrowing money and you have to pay interest on top of the money you've borrowed. So that's this idea of interest. Now, the idea of compounding. Interest is usually paid at the end of the year. So let's say you borrow some money and they're going to pay interest on that. And usually pay your interest at the end of the year. If you rent an apartment, you pay at the end of the month, but for a loan, you'd usually pay at the end of the year. But not always. They might want to have you pay the interest monthly, just like you would pay rent on an apartment. So in that case, they're going to have you pay in times per year. So this is how this thing works. P is the principal. How much you borrowed or how much you're lending to someone. R is the interest rate. This is usually called an annual interest rate. T, it's usually years. And N, well, just like you pay your rent monthly when you have an apartment instead of yearly, well, you might actually pay interest on your loan monthly or sometimes daily. I think student loans, the interest is paid daily. Now, what they actually do is they take your interest rate and they divide it by how many times you pay per year. This is usually an annual or yearly interest rate. And so when they charge you interest, say, per month, they would take that interest rate, divide it by 12, and then at the end of each month, that's the interest rate that they're going to use. The yearly rate divided by 12. So N is the number of times you're going to be paying some kind of interest throughout the year, where we say it's the number of times the interest is compounded. So that's what goes into this formula. So let me pull out an example from the text. And I think what I'm going to do, I'm just going to focus on section 1.5 today. We'll do 1.6 next time. I just want to make sure we go back and do some examples with the exponent rules, some tricky ones. So let's say we have this. So let's say you have $100 invested at 5.5% interest, compounded annually. How much is in the account after X years? All right. So you're going to invest $100 at 5.5% interest, and this is compounded annually. So how much is in the account after X years? Well, first off, some terminology. Annually, this is n equals 1. Semi-annually is n equals 2. Quarterly that's n equals 4. Monthly n equals 12. Weekly n equals 52. Daily's a weird one. And the reason daily can be a little tricky, it could be 365, or it could be 360. That's another story. There's another one called continuously, and if we have time today, I'll show you how that one comes about. So in our problem, we're compounding annually. So that means for us, n is equal to 1. Now, how much do we invest? $100. Principal? 100. Now, the interest rate is 5.5%. But what we're going to do is express this as a decimal. To convert a percent to a decimal, we move the decimal point 2 spots to the left. So you want to always convert your interest rate to a decimal. Now this is where they throw us through a loop. They didn't give us a number for years. It just said X. So what we're going to actually come up with is a formula that gives us how much we get from this account in terms of X years. So let's plug everything in. So we have our N, we have our P, we have our R, we have our T. And again, make sure this is decimal form. Just move this 2 over to the left. So we're going to get A is 100. And then we have X. So N is 1, R is 0.05. T is going to be X. So we're going to get 100, 1 plus 0.05 to the X, where A is 100, 1.05 to the X. And that's the best we can do. That's as far as we can go. So if we want to find out how much money we get from this investment in 10 years, place X with 10, and then we do the math. So I got to follow the orders of operation. A long decimal here. And that's approximately $162.89. And so that's how we would use that formula. Now, another one that comes up, let's say we have this. So any questions about that? Just sort of applying some knowledge with these exponents. So another one that came up, and this is a good one. Let's see. So for this one, we're going to look at radioactive decay for carbon-14. So carbon-14, it's is it an isotope? Is that what it is of carbon, the carbon atom? I think you get it in the atmosphere. As biological creatures, we ingest carbon-14. You can actually use it to try to date groundwater, oddly enough. But it decays, and you can look at it decays at a consistent rate. So if you look at the amount of carbon-14 in a biological remains, usually is what it is, or a creature for that matter, you can figure out when the creature had stopped ingesting carbon-14. In other words, it probably fell into a swamp and perished. And then based on how much carbon-14 is there, you can come up with some idea of how long ago this happened. So the idea is going to be this. To model the amount of carbon-14, we're going to use this. This is going to be our formula for growth and decay. And this is where that E is coming back. Now, for decay, K is less than 0. For growth, this might be something like with, let's say, bacterial growth. K is greater than 0. So for carbon-14, we're going to use a K equal to negative 1.2 times 10 to negative 4. So in other words, and then for X, going to be years. Let me just double check years or years ago. I'm going to say years. Let's say years. I'll be careful with this. I don't assume too much. So X is going to be years. So what could happen, we could ask this question. The reason I'm not going to say years ago is we could take carbon-14 accumulated right now. And then so many years into the future, how much is going to be left? So why 0? Is the initial amount of C14. And then Y, how much C14 is left. So the question we're going to ask is this. What percent of C14 is left after 866 years? We're going to use this model to figure it out. So what's going to happen we're basically just going to replace X with 866. Pardon me? There we go. So doing that, and if you crank the numbers, I want to do some intermediate steps here. you're going to get this. So you're going to multiply these together first. Negative 1.2 times 10 to the negative 4 times 866. You do those multiplications, you're going to get this. Now you've got e. So you got to take e, and this is usually something on your calculator, raise it to this power. So on my calculator, let's see, where did e go? There it is. If you do that, you're going to get y is y0 times 0.901297, approximately. So this is going to say that y is approximately 0.90 times the initial amount, y0, whatever that happens to be. But whatever we choose for y0, y is going to be 0.9 of it. So that means after 866 years, there is 90% of the initial amount of carbon-14. So what is this saying? Well, if we have a way of determining that 90% of the carbon-14 in something is still in there, and let's say you have some plant life or something, you're trying to date the plant life, and you're able to determine that of the carbon-14 in this plant, 10% has disintegrated, 90% is still there. Well, that's going to mean that this plant is 866 years old. So that's a way you can use carbon-14 to date things, provided that the model we used is correct. So any questions about that? So I just want to pick some examples with the laws of exponents. I do want to make one point about graphs. The textbook tends to not work with bases between 0 and 1. So what the textbook will do is this. If you have something like this, they'll rewrite it so you'll get, and then we distribute the x to the minus 1 as an exponent. And so they'll do something like this. So these mean the same thing. So when you see this in the textbook, they mean this. And so the graph for this is the same graph for this. It's the same graph. So you want to be careful with this. So in general, what the text is going to do they're going to use a base that's greater than 1. That's just something they're going to do. I'm just taking a look at the homework here. And yeah, when you're asked to graph these, they're always using a base greater than 1. But when they want to use really a fractional base between 0 and 1, they'll make the x a negative. So what you'll get is this. It's the same and again, if we have a greater than 1. So again, what this looks like oh, check this. So it's the same thing as this base here, because a is greater than 1, this whole base here is going to be less than 1. So that's just the approach they use in the textbook. Anyway, in our closing minutes, I just want to pick a real tricky question from the couple ones on the properties of exponents, just so we cover those. So let's say you have this. You need to simplify this. Well, first off, this exponent is distributed as an exponent. So you get 2 to the 4 over square root 2 to the 4. Now I want to go back to what the meaning of a root is. A root is a fractional power. So 2 to the 4 2 to the 1/2 to the 4. Now with this here, we distribute this as an exponent to that. We get 2 to the 4. We get 2 to the 1/2. And this time, it's multiplied. So we get 2 to the 4th over 2 squared. And then you can use the rule for subtraction. Same base means we can subtract. 2 to the 4 minus 2, which is 2 to the 2, or 2 times 2 is 4. And that's going to be our answer. Questions about that? All right. let's see. Get one more of these, and then that'll be it for today. So. So same base means we can subtract. So 5/3 minus 2/3, same denominator, so we just get 5 minus 2 over 3. Or the 3 over 3, which is 3 to the 1, which is just 3. That's it. So any questions about that? So that's section 1.4 and 1.5. I'll have to kind of, 1.6 is due Wednesday, I think. I might do some adjustment on that one. But that's 1.4 and 1.5. 1.6, it's inverse functions, logarithms, and then let's see, inverse trig functions. We'll finish that up on Monday. And then that's going to be it for chapter 1. So the plan is we'll do chapter 1, we'll do chapter 2, and then we'll look at our first test. So other than that, if you have any questions, let me know. I might have time to show you how you get the continuous compounding formula. That's kind of neat, but for another time. So other than that, have a wonderful afternoon. Have a wonderful weekend. Let me know if you have any questions. Other than that, take care.
Thank you. Thank you.
No?
I have a question.
Yes.
Is there a reason